All right, hey guys, Mr. Kyle, Myers Mathematics, and let's just jump right into it. So today I want to talk about, well, the same thing last week, basically. Envision 2020 Geometry. If you didn't see the video from last week, I'll put a link in the description below. But it's the end of topic 1, the review for all of the lessons in topic 1. So chapter 1, all the little, mini sections of chapter 1, basically. All right, so last week talked about, well, all the solutions to the first 2 pages, so pages 64, 65. And then today we're going to do pages 66 and 67. I blew them up a little bit because I noticed last week it was a little hard to try to fit things in there, and even when I was not writing very hard, it was still a little bit, the pen looked a little bit on the thicker side. So I figured I'd blow them up a little bit, and then that way when we're writing on it, it's not quite as big there. So let's go ahead and look at the first lesson of today, and that is inductive reasoning, aka patterns. So that's the key word. Inductive reasoning is essentially patterns. All right, you're looking for a pattern. So for instance, in the example it says make a conjecture, meaning a guess. These are all important vocab words, and you don't spell guess with a Q. Guess, right? It's like an educated guess, like a hypothesis in science class. Not to be confused with the hypothesis in this class. And then counterexample. So basically counterexample, and the reason why I'm even talking about all this vocab, by the way, so stick with me. Promise, I'm going to get to the solutions, but you do need to know the vocab because since there's a ton of vocab in chapter 1, teachers usually like to have a vocab quiz. So that's why I even bring up all these vocab words and talk about what they basically mean. So a conjecture is basically a guess, and then inductive reasoning is when you're looking at patterns. A counterexample, so you know what an example is, right? You give an example of something. That's not a definition, by the way, but you know what an example is. So, but you might not know what counter means because, besides the kitchen counter, you've probably never heard of that word used in this context before, and it's actually a little bit of an older English word. I wouldn't say Old English per se, but an older English word that means to go against. So when you argue with somebody, when you argue with your friend about, whether the green light is green, I don't know, that would be something I would argue about because I'm slightly colorblind, so it looks blue to me. But anyways, if you're arguing about something, then a lot of times your friend will say, hey, this is like this because I noticed a pattern of blah, 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 blah. And then you could be like, well, I've seen this happen, so you're wrong. For instance, if you're like a younger kid, you could be like, oh yeah, cats always have 4 legs. Duh, cats are supposed to have 4 legs. And then you could be like, well, I had a cat and it lost a leg, and now it has 3 legs. Trying to say I don't have a cat, right? So that would be a counterexample. Right, so important vocab words, but yeah, so let's go ahead and jump into the first number here. It says use inductive reasoning to find the next 2 terms in the sequence. So don't go crazy. You don't need to find the 3rd or the 4th or the 5th, just the next 2. And all we have to do is just kind of figure out what's going on. So the typical way to figure out a pattern in math is to figure out either what's being added each time or what's being multiplied each time. That's like a pretty standard way. Or you can figure out how much it's adding and then look at the pattern in how much it's adding each time. You can do that too. So for instance, 1, 2, 6, 24. Seems like it's getting pretty big pretty fast here. 1 times 2 is 2. 2 times 3 is 6. 6 times 4 is 24. 24 times 5 is 120. So if you didn't know this for sure, you could type it into a calculator. The reason why I went ahead and did multiplying first instead of adding or subtracting is because the numbers get big pretty fast. If it's adding each time, and you could try it. I mean, it would be, the adding would be, you'd have to add 1, then add 4, then add 18. So you could try to do it that way. But if you can't really see a pattern with adding, or if you look for a pattern within the pattern or whatever, then try multiplying, especially if the numbers get really big really fast like they did here. So it looks like the pattern is we multiply by a bigger number each time. a slightly bigger number, right? One bigger number than the last time. So that means the next one should be a 6. I would multiply 120 by 6. Right? So you can just kind of do this by hand if you want, or you can use a calculator. Depends on what your teacher is letting you do, whether you're in person or online. Obviously, if you're online, it's a little harder for your teacher to see if you're using a calculator. But that would be 12, and then carry 1, 6, 7, so 720. Okay. The other thing you could have done is done 6 times 6 and then doubled it. I don't know, math tricks. That's for another video. But that would be the next term. And we multiplied by 6, so next we would multiply by 7. Multiply by 7. 0, 7 times 2, that's 14. 7 times 7 is 49, plus 1 is 50. Ooh, that number got really big really fast. So those are the next two terms in the sequence, 720 and 5040. I'm going to go ahead and erase these since you have the ability to pause the video at any point and grab those answers. Okay, so number 28. And I'll go a little bit faster as I go here. I'm just kind of starting off a little slow. But if you need to skip to any point in the video, I don't take offense. You can just skip to whatever point you want in the video if you would like. Let's see. This doesn't look like it's increasing by that much, so it's probably adding. Let's try adding. So that'd be 2. If I add, I get 2. I'd have to add 3 there. Oh, but here I'd add 2. But here I'd add 3. Oh, that's weird. This is not like a strict algebra type sequence here, but it does look like the pattern is 2, 3, 2, 3. So I guess it would be 2, 3, 2, 3, 2, 3, 2, 3. You add 2, then you add 3, then you add 2, then you add 3. That's kind of an interesting pattern. It's a little easier to do than number 27, because then if I need to add 3 to get from 10 to 13, I just add 2, 15, and then I add 3, 18. That's not bad. That's nice. So that's the answer to 28. 29. We have 2, 5, 9, 14. Let's try to add. That would be 3. That would be 4. That's 5. 9 plus 5, right? 6. Oh, I see a pattern. Do you see it? Yeah, 3, 4, 5, 6. So next thing we would add would be 7, so 27. And then next thing we would add would be 8. 27 plus 8. 35. Okay, so that is the answer to number 29. For 30, again, it's not getting that big that fast. So again, I'm going to try to look for an adding pattern, not a multiplying pattern. 7 plus 4. There you go. So 17 plus 4 would be 21. Looks like I'm adding 4 again there. Adding 4. Oh, the pattern is definitely the same each time. That's weird. Normally the last number in a set of problems is the hardest one, but this one was the easiest one. You just add 4 each time. All right, 33 plus 4. Yep, 37. And then 37 plus 4. Yeah, exactly, 41. So that's the answer. Not bad at all. Okay, so then it says, find a counterexample to disprove each statement or support it with 4 examples. Okay, so counterexample, remember, counter means to go against, so you're using a go against example. So before, when I was talking about this, I used the example of cats always having 4 legs. And that's actually not true, right? A cat could have 3 legs. It would just, they're normally not born with 3 legs. I guess it could have been born with 3 legs if it had a deformity or something. But normally if a cat has 3 legs, it's because it lost a limb through, a cat fight or something. But anyways, counterexample, a go against example, an example to disprove, or support it with how many? Quattro. Okay, all triangles have 3 congruent angles. Well, what does congruent mean? The trick to these problems is always knowing what the vocab is. So you got to know what the math words mean. Congruent means the same. 3 angles that are the same. Well, there's really only one triangle that has 3 angles that are the same. And that's an equilateral triangle. Be like that. Every other triangle does not have 3 congruent angles. I could draw pretty much any other triangle. or even an obtuse triangle. So none of those would have congruent angles. Right? This one's a right angle. But there's all kinds of different triangles you could draw that don't have 3 congruent angles. Only one kind of triangle has 3 congruent angles, actually. So definitely draw a counterexample for that. Or you could just write a right triangle or an obtuse triangle, because there's no such thing as a right or an obtuse triangle that has congruent angles. Fun fact. 32. If p is an even number, then p plus 12 is even. Okay. P is an even number. Oh, did I? I was like, whoa, thought I erased the whole thing there for a second. Okay, so p is an even number. So let's think of some weird even numbers, because the trick to trying to find a counterexample is to think of like weird even numbers. I was about to say odd even numbers, but that would make no sense. So weird even numbers. So let's say like negative, a negative 2, or how about 0, or how about 6? And I only say 6 because 6 is 3 times 2, so it's not like 4 or 8 or 16 where it's like a bunch of 2's just being multiplied. It's 3 times 2. It's an odd number times an even number. Okay, so let's try to add 12 to these. If I add 12 to negative 2, I get 10. It's the same thing as 12 minus 2, which is an even number. Okay. 0 plus 12, that's 12. That's an even number. 6 plus 12, that's 18. That's an even number. It seems like there's no even number I could find to make that even. If you wanted to know for sure, you could do something super fancy, but I'm not going to show you the super fancy method because it's like way more mathematical than you need to know for this. But basically, there's no counterexample for 32. So I would just come up with one more example. Let's say 2 to make it easy. So this one would be 10. That's 12. That's 18. Add 12 to 2 and you get 14. So there's 4 examples to prove that it does, in fact, work. All right. Number 33, explain why only one counterexample is sufficient to disprove a statement, but one example is not sufficient to prove a statement. Okay, so this is more of like a vocab / conceptual question. The reason why you only need one counterexample is because when somebody makes a statement, they're saying that like that's always true. When you say something is true, what you mean is like it's always true. If I said George Washington was the first president, that's always true because it only is one event that happened in our history, right? The first president of the United States. So that's only one event that happened in history. I don't need to observe multiple events. There's only one event where that occurred, so I only need one event to prove that that's true. But if I said that if I square a number, then I get a positive number, or something like that, then what you're really saying is that every time you square a number, for every possible number ever, you get a positive number. So when you say something, like something is true, like you're kind of like you're saying it's always true, unless you add in like, oh, it's sometimes true that this happens, right? If you don't say sometimes or something like that, then you kind of are saying like, hey, this is always true. And if it's always true, then only one counterexample is sufficient. So that's why you would need. But one example is not sufficient to prove a statement. And actually, the best way to prove that something is true is actually by using deductive reasoning, not inductive reasoning. Inductive reasoning is something you can do to figure out a pattern, and then you use deductive reasoning to pack it up, which is actually the next lesson. Spoiler! But as far as an answer for 33, because you're probably like, what's the answer? Then what I would put is something like a statement. When you say a statement, you're saying it's always true, right? When you say a statement, you're saying it's always true. So you only need one counterexample. But one example is not enough. Something like that, okay? 34, the table shows how much Jack saves in his bank account each week. At this rate, how much will he save on week 10? Okay, so this is that pattern thing. This is basically, 34 is basically just a word problem version of 27 through 30. We just look for a pattern, and then we see how much he saves, and at the end or whatever, how much Jack saves in his bank account each week. So I think we're assuming that this is cumulative, meaning like he's saved a total of $350 in the second week. I think that's what we're assuming here. Otherwise, this problem would be a little bit harder. I don't think they're expecting you to do that. So 175. If I add 25 cents to that, I get $2. If I add $1 to that, I get $3. And if I add 50 cents to that, I get $350. So this is 175. Felt a sneeze coming on. Stupid allergies. Stupid ketchup. So 350 and 525. If I add 50 cents, I get $4. If I add $1, I get $5. So $1.50 so far, and then another 25 cents. So it looks like he saves $1.75 every week. So if he saves $1.75 every week, we could just take this table out to 10, 5, 6, ... 10, and you could do it that way. Or what you can do instead is you can just take the numbers and you can say like, okay, well, if it's 175 each week, week 1 is 175. Week 2 is 2 175s. 2 175s, 350, 175, 175. 3 on week 3. Oh, excuse the background noise. I think they're doing construction. So in week 3, you have 3 175s. You have 3 175s. So that would be 175, 175, 1. So if you think about it, the easiest way to do it would be to look for the pattern and then say, okay, well, if it's that many 175s, then I just need to multiply 10 by 175, which would be 17.5. 17.5. If you want to write it in money terms, you write a little zero on the end because that's $17.50. Ta-da! There's the answer to 34. All right, lesson 1-5. Conditional statements. Oh, these are so much fun. Fun. Okay, so quick review, blah, 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 blah. Okay, so the first thing is the hypothesis. P is normally you don't really need to know that P is the hypothesis. I mean, unless they expect you on the test to like write it in PQ form, and if they do, then you need to know that. But basically the first thing after if, you say if, and then you say the hypothesis. And then you take a pause. So in English, we write a comma. And then you say then. And then you say the last thing, which is the conclusion. Hypothesis, conclusion. So it's normally P arrow Q is how you write it. Converse, the best way to remember converse is like shoes, right? Converse shoes. You wear your left shoe on your left foot, and you wear your right shoe on your right foot. Right? Big brain stuff. So if you flip your shoes, right, like 2-year-olds sometimes do when they're first learning how to put their shoes on, they sometimes put their shoes on the wrong feet. Silly child. So what you do is you say, okay, well, the way I can remember converse then is if I put my shoes on the wrong feet. You put your left on your right and your right on your left. If it is what I like to call a strict conditional statement, which is a term that I made up that doesn't actually exist, then that means that when you do the converse, it doesn't make sense. Sort of like the opposite of a biconditional statement. If you do the converse and it does not make sense, or it's not always true, then that is what's called a strict conditional statement. Normally, statements are written so that they're strict conditionals. They're not done that way on purpose, I don't think, but if you write a conditional statement, it's not always true backwards, meaning the converse, right? Converse shoes. If it is true backwards, it's what's called a biconditional statement. Bi meaning two. It's true left, and it's true to the right. It's true if you put your left shoe on your left foot, and your right shoe on your right foot, and it's true if you put your shoes on the wrong foot. Okay? there's not really that many pairs of shoes where you put them on the wrong feet and they still fit right. So maybe this would be like if Converse made socks. I don't know if Converse makes socks, but if they made socks, it would be like Converse socks. Let's look at some examples because I'm doing a lot of talking and not a lot of examples. So let me show you some examples to make this make a little bit more sense. But basically, Converse are like shoes. Flip the shoes. Doesn't make sense. Inverse, letter N. That was a letter V. Letter, I can spell things. Letter N. The letter N for inverse, N for not. You take the opposite. So if there's already like a word, a not word in it somewhere, then you take it out. If there isn't one, then you put one in there. Wherever it seems to make the most grammatical sense, just, at some point in the hypothesis and the conclusion. But you do not flip them. The inverse is not flipped. Only the converse is flipped. If you do the converse and the inverse, if you flip it and you not it, then you get the contrapositive. Which sounds a little weird. Contra, like contradict, like to go against. But then positive, because if you flip the statement around and you change the word or the phrase to have the word not in it, then you're actually saying the same thing as the conditional statement. It's so weird. It's like how like two negatives makes a positive when you multiply? It's kind of like that. If you do the converse and the inverse, you get the contrapositive, which is basically saying the same thing as the conditional, right? In the book, it'll say that they have the same truth value, but they're the same. The conditional and the contrapositive should be the same, and the inverse and the converse should be the same, because you're either flipping it or negating it. You're doing this. Inverse, converse. Inverse, converse. All right. So anyways, truth value just means, hey, is it true or not? That's all truth value means. All right, for the vocab. So anyways, let's go ahead and get to the number 35. For each statement, write a conditional and the converse, inverse, and contrapositive. Okay, so I'm definitely not going to write this out by hand because that would take forever. So instead, I'm going to move this thing over. If it'll let me move, sucker. Ah, no. How dare you. All right, it's still doing that. Let me just grab my mouse real quick. Mouse time. All right, mouse. That way I can actually select it. Yeah, take that. Okay, so this is going to be really large print, so I'm probably going to make this smaller. But number 35, a number that is multiple of 4 is a multiple of 2. So first of all, let's rewrite this. A number that is a multiple of 4 is an if it's a multiple of 4, then it's a multiple of 2. Okay, so it makes sense to write it in if-then form first, because if it is written like this, then it makes more sense. I explained a thing with a thing. Anyways, so if you want to write this as the converse, remember converse shoes, left on the right, right on the left. So you still start with if, you always start with if, and then you always have the condition, or the conclusion. There we go, words. The conclusion after the then. So you always do that. So those words stay the same, you just flip the phrases. So if, and I'm going to do some big brain stuff here, watch this. If it's a multiple of 2, if it's a multiple of 2, then, oh, that's not how you spell it then, watch this, boom, hypothesis becomes the conclusion. Ta-da! All right, next. We do the not thingy. Let's do the not thingy. So basically I'm going to take this whole statement, this whole thing here. Remember, it's going to be in the same order. It's in the same order. So I'm just going to rewrite this whole thing. Let me zoom out a little bit. Actually, I could probably just take this and let's get the whole thing. Nope, that's not what I want. Doesn't look like can I change this? Oh well. Alright. Sometimes a little dumb when it comes to technology, which is weird because I really like technology, but sometimes I'm just really dumb when it comes to using certain things or figuring something out right away. Sometimes you just can't figure it out right away. Also, I just realized I copied and pasted that twice. So anyways, if it's a multiple of 4, then it's a multiple of 2. Wait, that's the original statement. I need to make that the inverse. So if it's not a multiple of 4, that's a good place to put a not. All right, if you've ever seen the movie Borat, which I probably wouldn't recommend because I'm pretty sure it had some bad parts in it. It's probably PG-13 or something, so I should probably put a disclaimer there. But if you saw the movie, basically one of the funny things in there that became a meme shortly afterwards was he never knew where to put the word not in a sentence so basically what I'm saying is this isn't an English class. If you wanted to, you could maybe put the not somewhere else and just for fun. If it's a multiple of 4 not, then it's a multiple of 2 not. You could put the not anywhere technically, but I'm going to go ahead and be good on this one at least and put the not where it seems to make the most grammatical sense. So it would make more sense to put it here. Not a multiple of 2. Okay, so let's make that a little bit longer so it's only one line. And then let's do this. So this statement right here that I just highlighted, that is the converse. Right? We flipped it around. Remember that? So if you do the converse and the inverse, you get the contrapositive. So all I need to do is say if it's not a multiple of 2, then it's a multiple of 4 not. There you go. Just for fun. Put the not right there. Okay, so if it's not a multiple of 2, then it's a multiple of 4 not. Okay? That is the converse. Left and right. Inverse would be, which one is the inverse? Oh, the next one here. If it's not a multiple of 4, then it's not a multiple of 2. That's the inverse. And then contrapositive is the last one. So the first one's the conditional statement written in if-then form. Next one is the converse. Next one is the inverse. Next one is contrapositive. Okay. Now, since there are, how many of these? Oh, there's only one more. We can go ahead and do that. Why not? All right, let me just select all of this. So I'll keep the if. Okay, there we go. Okay. So if Kona jogs 5, what? Write the statement, conditional, converse, and contrapositive. Okay, so this one's kind of annoying. It says Kona jogs 5 miles every Saturday morning. It's not really clear at first what he's talking about and how to write it as a conditional, because a conditional statement has to have a hypothesis and then a conclusion. There has to be some sort of thing that happens, and then as a result, something happens. So it seems like you could just say, if he jogs 5 miles, then it's Saturday morning. But actually, that doesn't make that much sense, because it says that he jogs 5 miles every Saturday morning, which means that if it's Saturday morning, then he will jog 5 miles. It's actually kind of reversed, because it says he jogs 5 miles, but the condition isn't that he jogs 5 miles. This one is tricky. I would see if your teacher's going to put this one on the test, because if so, you should probably get some more practice with this. But the condition here is that it's Saturday morning. If it's Saturday morning, in la mañana, then Kona Ice jogs, that'd be a cool name, your last name was Ice, then Kona jogs 5 miles every Saturday. All right, so that is a thing. Let's move this over a little bit, if I can. Here, what does this do? Text color, nah. No, it doesn't seem like I can change the text around that much. All right, anyways. So let's bring this out a little bit. What? Why is it not doing the thing? Do the thing. All right, we're just gonna zoom out a bit here. That way I have room for the other things. Okay. Oh my gosh. So here we go. You ready? We're going to go a little faster on this one since we spent a little bit of time on the last one. All right, so boom. This is this. If Kona jogs 5 miles every Saturday, so if Kona jogs 5 miles every Saturday, then it's Saturday morning. Select things. There we go. If Kona jogs 5 miles every Saturday, then it's Saturday morning. That is the converse. Next, we have the inverse. So I'm going to take the original statement again, paste it. If it's Saturday not morning, technically, if you want to really have the answer be grammatically correct, you should put if it's not Saturday morning. But at this point, I'm just kind of having fun. So I'm going to put Saturday not morning. If you want to, if your teacher doesn't think that's funny, then you should probably put the not after the it's. So go ahead and do that. And no, I wasn't talking to you, phone. Stupid Siri. So if it's Saturday not morning, then Kona not jogs 5 miles every Saturday. There you go. Oh, wait, hold on. Then it's Saturday. If Kona jogs 5 miles. Hold on. I messed up a little bit. Wait, hold on. Then Kona every Saturday. If it's Saturday morning. Oh, if it's Saturday morning, then Kona jogs 5 miles. Goodness gracious. I made a boo-boo. Hold on. If it's Saturday morning, then Kona jogs 5 miles. If Kona jogs 5 miles, then it's Saturday morning. There we go. Okay, I was wondering why that seemed a little off. Okay, if it's Saturday not morning, then Kona not jogs 5 miles. Much better. Okay. Sorry, made a boo-boo. Sorry, not sorry. No, but really though, yeah, so if you just want to be careful when you're writing these things out. Double, triple check, all that good stuff. But yeah, so conditional statement is the first line, second line is the converse, third line is the inverse, and we're about to write the contrapositive. If Kona jogs 5 miles. So remember, I just copied and pasted the converse statement, and then I'm going to put nots in it. If Kona, I'll write this one grammatically correct just for you. Doesn't, oh, if, I meant to put that here. If Kona doesn't jog, if Kona doesn't jog 5 miles, then it's not Saturday morning. Ha-ha! There we go. There's the contrapositive. All right. And there you go. There's the answer to 36. All right, sorry that took a little bit longer. Find the truth value of each conditional. Explain your reasoning or show a counterexample. So it's basically the same as the last section when they were talking about inductive reasoning. You just say if it's true or not, and then you say, hey, it's true because something, or hey, here's a counterexample. So it's essentially the same as the last section, but we'll go ahead and do it as well anyways. So let's zoom in a little bit. Okay. So if a number is less than 4, then it is prime. Well, this is sort of true, sort of not true. If we say a number, and you mean like a natural number, natural numbers start at 1 and count to infinity. Excuse me, there's a hiccup. So 1, 2, 3, 4, so on, so on. So those would be natural numbers. And yes, out of all the natural numbers that are less than 4, those are prime. But, so for prime numbers, it's true. So not prime numbers, gosh, I meant to say natural numbers. For natural numbers, numbers 1, 2, 3, it's true. For real numbers, and other number systems too, but I'm going to make this more simple than more complicated, but I wanted to go ahead and bring this up because it was a little vague. For real numbers, it's not true. Because in order for something to be prime, it has to divide by only itself and 1, and the result would have to be, that it would be a natural number or integer or whatever. So for real numbers, it's not true, but I think they mean just for natural numbers, because normally prime and composite numbers are only natural numbers. So maybe you don't need this part. Maybe that's too complicated. So for natural numbers, it's true, because the only numbers that are less than 4 out of the natural numbers are 1, 2, and 3. So 37 is good. I'm going to erase. If you need to go back a little bit and pause it, go ahead. 38. If 3x minus 7 is less than 14, then x is less than 8. Okay, well, let's just solve it, because that's basically what they're saying. If this, then that, and it's like an equation, so let's solve the equation. 7, add, 3x less than, 14 plus 7 is 21, and then we divide by 3, divide by trace, and I get x is less than 7. 21 divided by 3 is 7, not 8. Goodness gracious. So that is not true. Nope. If it snows, then school will be canceled. Well, I don't think that's true. I mean, I live in Florida, so if you're watching this video, I know maybe that's kind of weird for me to tell you that I live in Florida and I'm wearing a jacket. I just felt like wearing a jacket today, okay? So sometimes I just feel like wearing a jacket. Don't judge me. But I live in Florida, so it doesn't snow, but like once every 20 years or something, in like the Panhandle. But I think if it would snow, and it wouldn't be like a lot of snow, I don't think school would be canceled. If it's like flurries, like little tiny bits of snow, and it's not even like covering the ground or something, like I'm pretty sure school wouldn't be canceled just for that. Now, if there was like a snowstorm and you got snowed in, not to be confused with Edward Snowden, or whatever his first name was, I don't know. I don't keep up with politics, sorry. If it snows in the school, I don't think that's true. I don't think that's true, because if it is flurries is still considered snow, and the school would not be canceled. This one's not really a math question. That's just my opinion. So that's what I would put for that one. I would put false. Bear eats beets. So number 40, communicate precisely. A cafeteria only offers pudding on Tuesdays. Oh, pudding on Tuesdays. That's nice. Use this fact to write a biconditional about the pudding. Okay, so biconditional. We kind of talked about this earlier, but I didn't really talk about how to write it. You don't use if, then. You actually just write if and only if right in between the hypothesis and the conclusion. And actually, you know what I just realized? I don't want to write this whole thing out. I want to write using the text thingy. So, I did that again. Darn it. I had to click it with my mouse. There we go. Okay, so in order to write a biconditional, you write the hypothesis first without the if. You do not write if. You write if for conditionals, but for biconditional statements, you do not write the if. You just get straight to the point of the hypothesis. So the hypothesis in a conditional statement form would be something like, if it's Tuesday, then there will be pudding or something, right? So there will be pudding. There'll. Yeah, I'm pretty sure that's how you spell there'll. There will be pudding. There'll be pudding. If and only if. Okay, so the hypothesis was there'll be pudding. then we put the biconditional thingy, which is if and only if. You write if and only if exactly in between the hypothesis phrase and the conclusion phrase. And it doesn't matter which order because it's a biconditional statement. By the way, fun fact, there is no such thing as a triconditional statement. This was my favorite wrong answer as a teacher. Somebody put triconditional as an answer to something, and I laughed as I was marking it wrong. There's no such thing as a triconditional statement. They're still doing construction. How dare they? So rude. All right, so there'll be pudding. There'll be pudding. If and only if. What are they doing? Sorry about the noise. There'll be pudding. If and only if. Let's see. If and only if. Oh, it is Tuesday. It is Tuesday. There'll be pudding if and only if it's Tuesday. Oh, I should probably write that as a. It's Tuesday. There'll be pudding. Okay. So that is the answer to that. And now we are done with that page. Sorry that took so long. But, it is what it is. So let's get into 1-6 and 1-7 and 1-8. They're all kind of the same thing. You're starting to get into this thing called proofs. 1-6 is not really proofs just yet, but it's deductive reasoning, which is essentially what a proof uses. So one section kind of spills into the next. All right, deductive reasoning uses logical steps based on given facts to reach a conclusion and can be applied through laws of logic, such as the following. The law of detachment. If P, Q, and P are true, then Q is true. And then law of syllogism. Okay, so let's pause for a second. Law of detachment basically means that you write a conditional statement, and then the first thing happens, so the second thing happens. It's actually really, really straightforward and really basic, and I don't know why they even make this a thing, because it's really dumb, in my opinion, but basically it would be like this. All right, so at the time of me making this video, it is Tuesday. It is Tuesday. So, what time is it? Is it that time? Oh, it's that time already. Okay, so it is Tuesday at the time of this. And what that means is, actually, you know what? I'm going to have to probably wrap this up because I need to do something, and then I have to do something. Anyways, so what I'm going to do is I'm actually going to put this video into 3 parts. I thought I was going to have this into 1 part, and then I was like, no, let's do 2. And now I'm thinking this is probably going to make more sense if I do this in 3 parts. So I'm actually going to end this video for today. But I will do the other page either next week or very soon later on this week. But I normally have content at least every week on Tuesday put out at 4 ish, give or take, because YouTube is weird sometimes. But anyways, that's all for today, actually. So this has been Mr. Kyle, Myers Mathematics. If you haven't checked out my awesome free guide, go ahead and check that out. It's at myersmathematics.com.